Assalamu alaikum, brothers and sisters. Welcome to the journey of quest, where we quench your thirst of knowledge. Ever wondered how scientists determine the age of ancient artifacts and rocks? It's a question that might have crossed your mind as you marveled at a fossil or an age-old artifact. The answer lies in the intriguing world of radioactive decay. As you venture into the atomic realm, you'll find that radioactive decay is a naturally occurring phenomenon, a silent, invisible process playing out in the heart of atoms. It's a bit like a secret dance, a spontaneous transformation where an unstable atomic nucleus loses energy by emitting radiation, morphing into a more stable form. This process is random at the level of single atoms, making it unpredictable. Imagine a room full of popcorn kernels popping. You can't tell which kernel will pop next or when, but given enough time, you know they'll all eventually pop. Similarly, you can't predict when a single atom will decay, but with a large enough group, a predictable pattern emerges. And here's the fascinating part. This process occurs without any external influence. It's like an atomic clock, ticking away unperturbed by heat, pressure, or the passing of time. It's a process that's been happening since the dawn of time, and it's happening right now within the atoms that make up the world around us and even within our own bodies. This internal clock of atoms is what scientists tap into when they want to determine the age of ancient artifacts and rocks. By looking at the ratio of parent atoms, the ones that undergo decay, to daughter atoms, the ones formed from the decay, they can estimate how much time has passed since the material formed. It's like piecing together a cosmic puzzle, one atom at a time. So the next time you come across an ancient artifact or a piece of rock, remember the silent, invisible dance of atoms taking place within. Radioactive decay, then, is like a clock ticking away in the heart of atoms. So how does radioactive decay actually work? Well, it all starts with something called an unstable isotope. Isotopes are versions of an element that have the same number of protons, but different numbers of neutrons. This variety in neutron count can make some isotopes unstable, meaning they're not quite satisfied with their current state. These unstable isotopes, also known as radioisotopes, are like a group of people standing in a room that's just a little too crowded. They're not comfortable, and they're looking for a way to restore balance. To do this, they undergo a transformation, a process we call radioactive decay. Now, just like our imaginary room, the isotope doesn't become stable all at once. It's a step-by-step process where particles are emitted, energy is released, and the isotope gradually becomes a more stable version of itself. Let's imagine a party popper. You pull the string, and out comes a burst of confetti. In a similar fashion, an unstable isotope will pop to release particles and energy. These particles can be alpha particles, which are essentially helium nuclei, or beta particles, which are fast-moving electrons or positrons. Sometimes the isotope might even release gamma rays, which are high-energy packets of light. This party popper analogy isn't perfect, of course. A key difference is that while a party popper pops immediately when you pull the string, an unstable isotope decays at a rate that's not so predictable. You can't tell exactly when an individual isotope will decay, but you can predict how many in a sample will decay over a certain period of time. Each step in this transformation brings the isotope closer to stability, until eventually the isotope becomes a stable version of a different element. It's like our overcrowded room gradually emptying out until there's just the right amount of people left. In essence, radioactive decay is nature's way of restoring balance. Did you know there are 3 main types of radioactive decay? Yes, you heard that right. Our world, as intricate as it is, holds within it the fascinating phenomena of alpha, beta, and gamma decays. Let's start with alpha decay. This is a process where an unstable atom loses 2 protons and 2 neutrons, producing an alpha particle. The atom then transforms into a new element, 2 atomic numbers lower on the periodic table. Picture it as a party where 2 couples decide to leave early, changing the dynamic of the gathering. That's alpha decay for you. Next up, we have beta decay. Unlike alpha decay, beta decay involves a neutron in an atom's nucleus transforming into a proton, or vice versa. In the process, it emits an electron or its antiparticle, a positron. Think of it as a chameleon, changing its colors to adapt to its surroundings. In the atomic world, this color change is the transformation from a neutron to a proton or the other way around. Last but not least, we have gamma decay. This is the supermodel of decays. Why? Because it's all about energy and no particles are involved. When a nucleus is in an excited state, it can drop to a lower energy state by emitting a gamma ray, a form of electromagnetic radiation. It's like an overly excited person calming down, releasing their excess energy in the process. Now you might be wondering why these decays happen. Well, it all comes down to stability. The nucleus of an atom strives for a more stable state. If it's unstable, it will naturally decay, changing its form until it reaches a more stable configuration. Alpha, beta, and gamma decays are just different paths that it can take in this journey towards stability. So, there you have it. The three types of radioactive decay: alpha, beta, and gamma. Each unique, each fascinating, and each a testament to the intricate nature of our universe. These three types of decay are the means by which unstable isotopes regain stability. Now, how can we measure the rate of this decay? Welcome to the intriguing world of half-life, a fundamental concept in the understanding of radioactive decay. Picture this. You have a box of popcorn kernels. You heat them up, and they begin to pop. Now, you can't predict exactly when each kernel will pop, but you do know that over time, about half of them will have popped. This is the essential idea of half-life. It's the time required for half of the atoms in a sample to decay, just like half of your popcorn kernels popping. But let's be clear, unlike popcorn popping, radioactive decay happens on a much smaller scale and over a much longer time. We're talking about atoms, and these atoms can take anywhere from a few microseconds to billions of years to decay. That's right, billions of years. Half-life is a probabilistic concept, not an absolute certainty. It's a bit like flipping a coin. If you flip a coin 100 times, you can't predict the outcome of each flip, but you can predict that about half the time, it'll land heads up. Similarly, we can't predict precisely when a particular atom will decay, but we can predict that after one half-life, about half the atoms in our sample will have decayed. And the beauty of it all? Each radioactive isotope has its own unique half-life. This characteristic half-life is what allows scientists to use radioactive decay as a sort of atomic clock. By measuring the amount of parent and daughter isotopes in a sample and knowing the half-life of the parent, scientists can calculate the age of rocks and minerals, unravel the history of our planet, and even gauge the age of the universe. So remember, half-life isn't about predicting the exact moment an atom will decay. It's about understanding the probabilistic nature of decay over time. It's about the ticking away of atomic kernels, the very essence of time on a subatomic level. Half-life is the ticking rate of our atomic clock. So what happens when an isotope decays? This intriguing question opens the door to the fascinating world of radioactive decay schemes. Picture a family tree, but instead of grandparents, parents, and children, we have parent isotopes and daughter isotopes. In these decay schemes, a parent isotope decays into a daughter isotope. Now here's the kicker. This daughter isotope may itself be unstable. It's like a domino effect, where one unstable isotope topples over to become another, which then topples over to become yet another, and so on. Each step in this cascade of decay is called a decay series. Let's consider an example to illustrate this. Uranium-238, a naturally occurring isotope, embarks on a long journey of decay, transforming through several steps into Lead-206, a stable isotope. Along the way, uranium-238 becomes thorium-234, which then becomes protactinium-234, and the list goes on. This radioactive relay race doesn't happen randomly. Each step follows a specific pattern, a decay scheme, governed by the laws of physics. The parent isotope and the daughter isotope. The type of decay and the half-life of the parent isotope are all part of this scheme. Interestingly, not all isotopes follow the same path of decay. Some may have a straightforward decay scheme where the parent isotope decays directly into a stable daughter isotope. Others may have a more complex scheme involving several steps before reaching stability. Understanding these decay schemes is crucial in many scientific fields. For example, in geochronology, they help us determine the age of rocks and minerals. By knowing the half-life of the parent isotope and the amount of daughter isotope present, we can calculate how long the decay process has been going on. But that's not all. Decay schemes also shed light on the processes that formed our planet and continue to shape it. They're like the DNA of the Earth, holding clues to its past, present, and future. These decay schemes are like a family tree for isotopes, showing their lineage and history. Just as we trace our roots to understand our heritage, scientists use decay schemes to understand the heritage of our planet. So, the next time you see a rock, remember that it holds a story of decay and transformation that spans billions of years. Now, how can we use radioactive decay in real-world applications? Well, one of the most fascinating applications of radioactive decay is in the field of geochronology, the science of determining the age of rocks, fossils, and sediments. And it's all thanks to certain isotopes and their tendency to decay over time. You see, some isotopes found in nature are unstable or radioactive, and over time they decay into other stable isotopes. This process of decay occurs at a constant rate, known as the half-life of the isotope. It's this predictable rate of decay that scientists use as a kind of natural clock to determine the age of various geological materials. For example, one of the most commonly used isotopes in geochronology is potassium-40. This isotope decays to argon-40 at a predictable rate, with a half-life of approximately 1,300,000,000 years. By measuring the ratio of potassium-40 to argon-40 in a rock sample, scientists can calculate when the rock was last heated, which resets the radioactive clock. This technique, known as Potassium-Argon dating, is especially useful for dating volcanic rocks. Another popular radioactive dating method is radiocarbon dating, which is used to date organic materials. This method relies on the decay of carbon-14, a radioactive isotope that is continuously created in the atmosphere by cosmic rays. Since all living organisms absorb carbon-14 while they're alive, by measuring the remaining amount of this isotope in a sample, scientists can figure out when the organism died, and hence, the age of the sample. But these are just a couple of examples. There are many other isotopes and decay schemes used in geochronology, each suited to different types of rocks and different time scales. From the ancient zircon crystals that hold the record of Earth's earliest days to the young corals that reveal the recent history of our climate, radioactive decay helps us decipher the story of our planet. Radioactive decay, then, is a time machine allowing us to journey into the past. But the uses of radioactive decay don't stop at dating rocks. Radioactive decay is not just a geologic clock, it's also a fundamental tool in studying petrogenesis, a fancy term for the origin and evolution of rocks. By understanding the isotopic compositions of rocks, we can uncover intriguing details about the nature of our planet's past. Let's break this down. Isotopes are versions of an element that have the same number of protons, but different numbers of neutrons. These isotopes decay at a predictable rate, a fact we use to our advantage in geochronology. But the isotopic composition of a rock isn't just about the ticking clock of decay. It also provides vital clues about the rock's history. Imagine a detective piecing together a case. The isotopes are the clues, the evidence gathered at the scene. Each one tells a unique story, a tale of transformation and change. The detective, in this case the geologist, interprets these clues, building up a picture of the rock's past. For instance, the isotopic composition of a volcanic rock can reveal the nature of the mantle source that melted to form the magma. Analyzing the isotopes of strontium, neodymium, and lead in a rock can provide information about the time and nature of magma mixing events. Similarly, the isotopic composition of a metamorphic rock can indicate the temperature and pressure conditions of metamorphism. This can help us understand how mountain ranges were formed and how tectonic plates interacted in the past. Radioactive decay also helps us trace the path of a rock from its birthplace deep within the Earth's mantle, through its journey to the surface, and even its alterations on the surface due to weathering processes. So you see, radioactive decay isn't just about time, it's also about origins, journeys, and transformations. It's about piecing together the complex and dynamic history of our planet from the clues that lie within the rocks beneath our feet. Radioactive decay, therefore, is also a detective, helping us uncover the secrets of Earth's geologic past. We've come a long way since asking how scientists determine the age of ancient artifacts and rocks. Let's revisit what we've discovered so far. Radioactive decay, a process that occurs naturally in unstable atomic nuclei. We've learned about its three types: alpha, beta, and gamma decay, each with unique properties and effects. We've delved into half-life, the time it takes for half of the radioactive atoms in a sample to decay, a fundamental concept in understanding the age of our Earth. We've explored decay schemes, the series of transformations that radioactive elements undergo, leading us to the marvels of geochronology and petrogenesis. Geochronology allows us to date rocks and minerals, while petrogenesis reveals the origin and formation of these geological structures. Indeed, the power of radioactive decay lies not just in its atomic transformations, but in the stories those transformations can tell us about our world. Thanks for watching us share our videos, subscribe our YouTube channel, and press the bell icon, and stay curious for new uploads.